All right, let's talk about rotation in Unity. If you've ever spent hours, maybe even days, fighting with a camera script or trying to get a turret to aim just right, you know this can be, well, a huge pain. Today, we're going to pull back the curtain and make it all make sense.
So, why is this so hard, right? You write what feels like perfectly logical code to make an object face a target, and instead of a nice smooth turn, it's all jerky, or it just randomly flips upside down. It's a classic headache for pretty much every Unity dev, and it almost always comes down to one single sneaky problem. And that problem has a name: gimbal lock. You know how we usually think about rotation with x, y, and z values? Those are called Euler angles. Well, sometimes two of those axes can line up perfectly, and when they do, you basically lose a dimension of movement. Your object gets stuck, and there's no way to get that smooth, predictable rotation you're looking for. It's the absolute enemy.
But before we can actually defeat gimbal lock, we gotta understand the world we're working in. And in 3D, that all starts with coordinate space. You see, where an object is and how it turns depends entirely on your point of view.
This table breaks down the two big ones you need to know. First, you've got global space, or world space. Think of this as the absolute, unchanging map of your entire scene. The center of the universe is always at 0, 0, 0. Then you have local space. This is a coordinate system that's relative to an object. Its origin is the object's own pivot point, and its axes, its own personal sense of forward, up, and right, move and rotate right along with it.
Here's a super simple way to get it. The room you're in right now, that's your global space. Now, put a table in the middle of that room. That table has its own local space. If you put a cup on the table, the cup's position can be described relative to the table. So what happens when you slide the table across the room? The cup moves with it, right? Even though its local position on the table never changed. That's the difference right there.
Okay, so we understand our space. Now let's meet the hero of this story, the thing that's going to solve gimbal lock and all of our rotation nightmares. Let's talk about quaternions. So a quaternion is how Unity actually thinks about rotation under the hood. It's this mathematical thing with 4 parts: x, y, z, and w. Now the math behind it is, let's just say, it's pretty heavy. But here's the best part. You don't need to understand it at all to use it. All you need to know is that it represents one complete, clean rotation. And most importantly, it is physically incapable of having gimbal lock. So this is maybe the most important rule of all. You almost never, and I mean never, try to change the x, y, z, or w values of a quaternion yourself. They just don't make sense to us like angles do. Instead, we're going to treat the quaternion like a kind of magic black box and use Unity's amazing built-in functions to do all the work for us. And that brings us to the really good stuff. Let's build your toolkit. We're going to walk through the C# code for the most essential quaternion functions that you will use over and over again. First up, Quaternion.LookRotation. This is your go-to for making something instantly snap to face a target. So let's look at this code. We've got a public transform target up top. That just gives us a little slot in the Unity inspector to drag our target object into. Then all the action happens in update, which, as you know, runs on every single frame. Okay, let's break down that update method line by line. First, vector3dir equals target.position minus transform.position. A little vector math here. If you subtract your start point from your end point, you get a vector that points from start to end. So this line gives us the exact direction from our object towards our target. Next, quaternion row equals quaternion.LookRotation dir. We just feed that direction into the LookRotation function, and like magic, it spits out the perfect quaternion rotation to face that way. And finally, transform.Rotation equals rot. We just assign our new rotation, and boom, done. Now, LookRotation is instant, which is great sometimes. But what if you want a smooth, steady turn, like a big heavy turret or a security camera? For that, we use Quaternion.Rotate towards. Looking at this script, we have a target rotation and a speed, which we've set to 50 degrees per second. The real magic, though, is that single line and update. Let's pull that line apart. Rotate towards needs 3 things. First, where are we starting from? That's our current rotation, transform.Rotation. Second, where are we going? That's our target rotation. And third, what's the fastest we can move this frame? That's speed times time delta time. And this is so important. Multiplying by time delta time makes our rotation frame rate independent. It turns our speed from degrees per frame into degrees per second. So it'll be just as smooth on a super fast gaming PC as it is on an older laptop. All right, tool number 3 is probably the one you'll see the most for smooth rotation, Slerp. It stands for Spherical Linear Interpolation. Sounds fancy, but it just smoothly blends from one rotation to another.
In this script, we're actually combining what we've already learned. Inside update, we first use LookRotation to figure out where we want to be pointing. Then, on the next line, we use Slerp to move from our current rotation towards that target rotation. This gives you a really nice, natural-looking ease-in and ease-out effect.
So you might be asking, wait, why Slerp? What about Lerp? It's a great question. Lerp, or linear interpolation, moves in a straight line. That's perfect for positions or colors. But for rotation, a straight line can look weird and cause the speed to change. Slerp, on the other hand, travels along the shortest arc on a sphere. This guarantees a constant, smooth rotational speed, which is exactly what our eyes expect to see. The takeaway is simple. When you're dealing with rotations, you want Slerp. Okay, you've totally got this. You can create rotations, you can move between them smoothly. Now it's time for the pro-level stuff, layering multiple rotations together. So, let's say you want to turn an object 45 degrees sideways and then tilt it 30 degrees down. How do you combine those? It's surprisingly easy. You just multiply the quaternions. That's it. The little star, the multiplication operator, is set up in Unity to just combine the effects of two rotations into a single new one. But, and I really can't say this loudly enough, when you multiply quaternions, the order is absolutely everything. This isn't like normal math where 2 times 3 is the same as 3 times 2. With quaternions, A times B is not the same as B times A. And here's the part that gets everybody at first. The order feels backwards. When you write rotation 2 times rotation 1, you'd think it applies rotation 2 and then rotation 1. Nope, it's the other way around. The rotation on the right side of the star happens first, and then the rotation on the left. So rotation 2 times rotation 1 means apply rotation 1, and then to that result, apply rotation 2. Remembering that little detail will save you so much confusion. And believe it or not, that's really it. We've gone from the core problem of gimbal lock to the solution with quaternions and all the way to combining them. You honestly have a new superpower for your Unity projects now. So let's just recap the big ideas one more time. 1. Quaternions are the answer to gimbal lock and smooth rotation. 2. Don't touch their x, y, z, w values. Use Unity's functions like LookRotation and Slerp. 3. To combine rotations, just multiply them. And 4, the most important one to remember, order matters. B times A means do A first, then B.
With this toolkit, you can build just about anything. Complex aiming systems, procedural animations, really smart camera controllers. The possibilities are huge. So the only real question left is, what's the first cool thing you're going to build? Get in there and start playing around. Thanks for watching.